Grok Build is SpaceXAI's terminal AI coding agent. It is a Rust workspace designed to run in diverse environments, from standard headless servers to local text user interface pagers. While the large language model at the center provides the completions, it is one component of a larger system. To see how an agent actually functions in a live environment, we have to look at the surrounding architecture, how it curates context, limits execution, and manages state. We can map this architecture by following its spine. We are going to trace the exact architectural path a single user message takes through this spine, from raw input, through the context gates, and out into execution. A production environment presents three specific risks that a simple completion loop cannot handle: thread collisions that tear the state, history bloat that exceeds the context window, and long-running shell scripts that lock the execution thread. These failure states are not model problems, they are architectural problems. This video analyzes how the harness is structurally designed to defend against them. The defense against state corruption starts at initialization. When Grok Build spins up, it generates an agent configuration that remains strictly immutable throughout the session. The entire mutable history of the conversation is isolated inside a ChatStateActor. This is a dedicated asynchronous Tokio task. It holds a monopoly over the conversation state. To prevent race conditions, frontends cannot directly modify the conversation history. Instead, they format queries as strictly typed chat state command units and push them into a sequential queue. This creates a literal mailbox. The ChatStateActor drains these commands one by one, reading and writing in a single thread of execution. Even if multiple frontends send queries simultaneously, they wait in line. Standard web architectures often scatter shared mutable state across multiple functions, relying on complex mutex locks to keep data consistent under load. Grok Build's actor model creates a lock-free foundation for state tracking. By funneling every read and write through a single sequential mailbox, the harness makes state corruption mathematically improbable. Once the state is stable, the system must generate a prompt. The single door between the raw conversation history and the LLM is a function called build conversation request. This function enforces a context budget through three gates. First is pruning. When token utilization crosses 50% of the total context window, the harness strips the oldest tool results out of the conversation payload. The second gate manages image data. Because images are the heaviest part of any payload, the system enforces a hard 50 megabyte limit on the total request body. As the user and agent exchange files, the payload approaches the ceiling. When it reaches a 47 megabyte high watermark, the eviction protocol initiates. Instead of clearing the trigger by a minimum amount, the harness initiates a batch eviction, dropping the payload to exactly 25 megabytes, half the total capacity. This logic is built around hysteresis. If the system only cleared the 47 megabyte threshold, the very next turn would recross it. That would force the system to rewrite the prompt every turn, which repeatedly busts the KV cache prefix. By dropping the payload to 25 megabytes in a single batch, the system buys massive overhead. The prompt prefix is rewritten once, allowing the cache to remain warm and performant across the following turns. Effective production inference relies on treating the context window as a strictly budgeted, cache-optimized space. After the LLM processes that budgeted request, it outputs intent. The harness maps this intent to model-facing tool names, such as run terminal command. The tool bridge component receives this intent and maps it against the authorized toolset. This creates a fundamental deadlock risk. While a shell script is executing, the tool registry itself is locked by that call. To maintain system responsiveness, Grok Build stores the terminal handle as a separate field, completely outside the registry lock. This structural bypass allows a kill foreground commands function to reach the terminal immediately. The harness can terminate a runaway execution without waiting for the deadlocked registry lock to release. Ensuring a user can interrupt an autonomous loop requires architecting physical bypasses around the agent's own execution state. While Grok Build is a single agent system at the session level, it achieves complex tasks through a parallel orchestrator mode. The orchestrator's behavior is enforced through tool denial. It is explicitly stripped of all file editing tools. It has no physical way to modify a codebase. The system prompt instructs the orchestrator to act as a technical lead. Because it cannot edit files directly, it is forced to delegate modifications to subagents via the Spawn subagent tool. There is no harness-level routing engine making parallelization decisions. The LLM reads the constraints in the prompt and chooses the mapping based on its instructions. Each subagent the orchestrator spawns creates an entirely new session, complete with its own isolated ChatStateActor and mailbox. Hard tool constraints and rule-based prompts create a multi-agent system that is more robust than a brittle external code planner. External digests of Grok Build frequently label its memory as a weak primitive, assuming that all facts evaporate when a session ends. We can verify the actual capability by checking the Rust source code for the XI Grok memory module. Behind an experimental flag, the harness provides a persistent 3-tier markdown store. It organizes knowledge globally, per workspace, and per session. The system uses a SQL-like index blending BM25 keyword search with vector k-nearest neighbor retrieval. A consolidation pass called AutoDream regularly distills raw session logs into curated knowledge tiers. Evaluation requires analyzing the underlying database architecture and experimental limits alongside the default deployment behavior. Our trace of the data flow reveals 3 critical architectural safeguards. First, Grok Build maintains state safety by using a strictly serialized actor model mailbox rather than shared locks. Second, it protects inference speed by treating the context window as a budgeted artifact, using hysteresis to defend the KV cache prefix across multiple turns. Third, it generates complex orchestration by using tool denial to force the model into parallel delegation. LLMs provide the intelligence, but the harness provides the autonomy. The capability of an agent is defined by the physical architecture of its gates, its locks, and its buffers.